Today we study differential forms. Differential forms are an important part of our course. They're essential in studying smooth manifolds and curved spaces. Okay, let's start with a quick review of things we discussed in the previous lecture over vector spaces. So we discussed multilinear maps and tensors over vector spaces and over Euclidean spaces, right? So let's do a quick review. Okay, let's say V is a finite dimensional vector space. Okay, so we know any finite dimensional vector space is essentially isomorphic to some Rm, any vector space over R. So let's say it's isomorphic to Rm for some integer, positive integer m, or non-negative integer m. Okay, let's say T is a K tensor over V star. So it means it's a K linear map from V times V times V K times to R. Okay, so this is a map which is linear in each V, in each component. So we have K times V and it's linear in each of them. We say V is alternating as a K-linear map is alternating. If we change the location, the place of the inputs, the vectors V1 up to Vk, if we change their location by a permutation sigma, the value of t on them would change by a sign, right? And that sign would be the sign of sigma. Okay. So we denote the space of alternating K-forms with lambda KV star. And we call T a K-form on V. Okay, great. So these are the things we discussed. Note that V is a finite dimensional vector space, so it's generated by a basis. Let's denote the elements of the basis by E1 up to En. We have a dual space denoted by V star, the set of linear maps from V to R. There's a dual basis for that. Again, I denote them with E1 up to EM. I use superscript rather than subscript. So EI is the linear map which sends EJ to 0 if I and J are different numbers. And it sends it to 1 if I equals J, right? This is the definition of dual vector space. And this is the kind of dual basis for the dual vector space. Okay, great. So fixing a basis for V, we learned it gives us a basis for lambda KV star. Lambda KV star is generated by the wedge product of K elements of the basis. So let's say EI1 up to EIK are K elements of the basis. So I1 is less than I2, let's say up to IK. Let's fix K numbers between 1 and M. They should be distinct. So if you look at the wedge products of these, you get a basis for lambda K V star. So if T is a K form, it should be possible to write T in terms of these elements. So T should be a linear combination of EI1 wedge EI2 up to EIK. So there should be some real coefficients. We denote these real coefficients by TI1 up to IK. So the sum is over I1 up to IK. I1 up to IK can be any K distinct numbers between 1 to M. And we assume they are ordered. Right. Okay. Now, we want to extend our discussion from vector spaces, from Euclidean spaces like V and Rn, to smooth manifolds. So we want to replace V by a manifold M. Okay? So the way to do it is that, let's say we have a smooth M-dimensional manifold. Let's denote this manifold with M. Okay, let's say we have our manifold M. Schematically, let's say this is our manifold, some higher dimensional manifold, right? It can be of any dimension. So for any point x we pick inside the manifold, We know by the definition of smooth manifolds, there's a local chart around it, right? There is some open set U inside M containing X, and a map phi diffeomorphism to some open subset in Rm. We can take that open set to be the whole Rm, right? Phi inverse would be a diffeomorphism from Rm to the open set U. Okay. Now look at Rm. Well, this is a finite dimensional vector space. It has a basis, right? Let's say E1, up to Em, a basis for Rm. In fact, we can move this basis to any point inside Rm. We can move it around. We don't need to think about it as fixed at the origin. Now, think about derivative of phi inverse. It acts on E1 up to Em at any point, for instance at 0 or any other point. It would send these back to some vectors inside the manifold M. Let's denote these vectors with partial x1 up to partial xn. So these partial x1 up to partial xn would be those small red vectors tangent to the manifold M, say at the point x. Okay? So this way we get M tangent vectors, M vectors tangent to the manifold at the point x. Let's say schematically this plane is the tangent space to M at the point x. Now this vector space is generated by partial x1 up to partial xm. So more accurately, partial x1 up to partial xm form a basis for tangent space of M at the point x. Right. Okay. So now this is a point-wise discussion. We have a vector space, tangent space of M at x. Just like when we were working with other vector spaces, we can look at the dual of this vector space. The dual of the tangent space of at M at x, Txm star, usually is denoted by T star of M at the point x. So we just move the star in front of T. This space is called cotangent space of M at the point x. So rather than tangent space, now that we are looking at the dual, we call it cotangent space. Okay, so cotangent space is the dual of the tangent space, right? Okay, so this is essentially just as we defined before for any linear space, this is the set of linear maps from tangent space of M at x to R. Now, for tangent space, we found a basis for the tangent space of M at x, right? We said partial x1 up to partial xm form a basis for tangent space of M at x. Now, just like what we discussed before, you can define the dual basis for the dual vector space. So T star of M at x is generated by the dual of partial x1 up to partial xm. We denote these dual covectors by dx1 up to dxm. So each dxi is a linear map. How do we define it? It's a linear map. I should only define the value of dxi on the elements of the basis of tmx. So I should say what is dxi of partial xj. Dual means I define it to be 0 if I is not equal to j and 1 if I equals j. This is the definition of dxi for us. Okay, with this definition, dx1 up to dxm form a basis for T star m. Using that, just like the case of linear spaces, we can construct a basis for lambda k T star of m at x. They are generated by the wedge product of these linear maps. So dxi1 wedge up to dxik for some set of ordered set of indices i1 up to ik. Right? This is just the way we defined a basis for lambda k v star, right? So here T star of m at x plays the role of v star. And dxi1 is like ei1 up to eik. So we are just doing what we did earlier before for any vector space v. We are doing that for tangent space of m at x. Great. Now you see, for any point x in M, we pick, we can think about a linear form, a linear K form, alpha in lambda kt star of m at x, right? So just as we discussed, alpha can be written as a linear kind of combination of the elements of the basis. So it should be sigma some coefficients dxi1 which up to dxik. And let's denote these coefficients with alpha I1 up to ik. These are just real numbers. But the point is that we can do this for every x in M. So suppose I have such a form, linear form, on tangent space of M at x for every x. So for every x, alpha of x is such an object. Now, as I move around x, it looks like a function. The value would change. It would depend on x. So the coefficients alpha I1 up to ik, rather than being real numbers, they're functions of x. So to kind of mention that and emphasize on that, I would write it as alpha I1 up to ik of x. So I think about these as functions, let's say, defined on some open neighborhood u around x to r. Okay, this object, which is essentially by putting together all these linear forms on tangent spaces and defining it over an open set, I call it a differential form. So I call it a K form or a differential form of degree K. Okay, great. So that's our definition of differential form. So at each point x, this would be a linear K form on tangent space of M at the point x. Okay, so for each x in M, alpha of x would be lambda k t star of M at the point x. So for each x, we have one of these linear objects. We're just putting these all together. We're gluing these all together. We denote the set of k forms on a manifold M with omega k of M. So this is our notation. Omega k of M would be the set of linear K forms on each tangent space linear, but now when we glue it and put it all together, this is not a linear object anymore. So if K equals to 0, omega 0 of M, it's just a kind of notation thing. It makes more sense to define it this way. Is defined as the set of smooth functions on M. We denote it by C infinity M. If K is larger than the dimension of the manifold, this space is just 0. It's essentially trivial, does not have any object. 0 is usually understood as K form for any K. The degree of K is not kind of well defined. You can think about it as K form for any K. There are two important things about differential forms, two important operations on differential forms to learn. The first one is called exterior derivative, which is kind of like taking derivative of functions. It's more suitable to work with differential forms. We denote it with D. D is like a linear map which takes a K form and gives you back a K plus 1 form, where here K can be any integer, or say non-negative integer. So let's consider the simplest case where K is 0. So if D acts on 0 forms, it should give you 1 forms. It increases the degree by 1, right? But we said 0 forms are essentially just smooth functions on the manifold. So say input would be something like f, where f is a smooth function from M to R. D of f should be a 1 form. We define d of f by the following. We simply define it to be partial derivative of f with respect to xi dxi. This is kind of a coordinate dependent definition. But in fact, it's well defined. It doesn't matter which coordinate you pick. Partial f partial xi is a real valued function. At each point x in, say, some open neighborhood u on the manifold, this derivative of f with respect to xi would be a real valued function. dxi is a 1 form. So the product after taking some gives you another 1 form. It's a good exercise to see this is a well-defined definition. Now, to extend it to other higher degree differential forms, we use a few rules. So the first thing is that d of sum of two forms is the sum of their exterior derivatives. But the essential thing to extend it to other forms is what is the wedge product of two forms. Note that when we have, say, a K form on the manifold alpha and another form, say L form on the manifold beta, we can define their wedge product. Why is that? For linear spaces, vector spaces, we define the wedge product of forms. Now here we can do the same. We can do it at each point. We have two linear forms on the tangent space. We can look at the wedge product and extend it all over the manifold. So the product rule we use is that d of alpha wedge beta would be d alpha wedge beta plus minus 1 to the k, where k is the degree of alpha, times alpha wedge d beta. The next rule is that d of something equals 0. So briefly, we can say d squared equals 0. For instance, d of dxi is 0. This implies d of dxi wedge dxj is equal to 0. We can use the fact that d squared is 0, and we have a formula for d of alpha wedge beta. If you put these together, you can say d of dxi wedge dxj equals 0. And then by induction, you can see you can extend this to a larger number of wedge product of dxi. So if I have dxi up to dxk, their d is still 0. Okay, so these all follow from the two facts we mentioned above. So maybe let's do an example. Let's say f is a real valued function on a manifold M. Let's consider two form, f dx1 dx2 plus d g dx2 dx3. Let's say the manifold has only three, it's three-dimensional. Locally, it has three coordinates, x1, x2, x3. What is d of exterior derivative of this form? So I should have d of f, wedge dx1, wedge dx2 plus f, d of the rest, which is dx1, wedge dx2. So I broke f dx1, wedge dx2 into two parts. Now for the second part, I have d of g dx2 dx3 plus gd of the rest, which is dx2 wedge dx3. Now we learn d of dx1 wedge dx2 is 0, d of dx2 wedge dx3 is 0. So what remains is d of f wedge the rest plus d of g wedge the rest. What is d of f? Partial f with respect to x1 dx1 plus partial derivative of f with respect to x2 dx2 plus partial derivative of f with respect to x3 dx3. Wedge, again the rest, which is dx1 wedge dx2. We do the exact same thing for the function g. We write the definition of d of g there, and then we have wedge dx2, wedge dx3. Okay. Now, recall that we had this for linear spaces. We have it here for forms too. dxi wedge dxi is 0. It follows from the anti-commutativity of differential forms. This implies if you have dxi wedge some other forms, again wedge dxi, you again would get 0. You can kind of change their places until you bring dxi, wedge dxi next to each other, and that would be 0. So using that, you can see partial 1 f dx1 wedge dx1 dx2 is 0 plus partial 2 f dx2 wedge dx1 dx2 is 0 because again we have two dx2s. So the only thing which remains is the derivative of f with respect to x3 dx3 wedge dx1 wedge dx2. Kind of same argument applies to g, only the first term survives. We have partial x1 g dx1, wedge dx2, wedge dx3. The other terms, we get again repetitive dx2 or repetitive dx3, so they would vanish. Also, I can change the order. dx3, I can move it over dx1. It would produce a minus sign. And then I can produce it also over x2, it would produce another minus sign, and these two minus signs would cancel each other. So if we do so, we get partial 3f dx1 dx2 dx3 plus partial 1g dx1 dx2 dx3. I can factor out this dx1 dx2 dx3. I would get the following, which is the simplest form of this expression. Right, so this is a good exercise. We would do such computations again a lot in this course. So the other essential thing is that for any vector field, previously we defined on linear spaces, essentially for any vector, we define interior product. Now, here on manifolds, we should replace that by vector field. Let's say V is a vector field on M. Interior product with V gives a map from K forms to K minus 1 forms for any K. So unlike exterior derivative, which kind of adds the degree by 1, here it reduces the degree by 1. For any K form alpha, iota V alpha would be a K minus 1 form. This is interior product. So what is the definition? For any x in the manifold, I should tell you what is iota V of alpha at the point x. It's supposed to be a K minus 1 form. So at any point x, it would be inside lambda K minus 1 T star of M at x. So if it's in lambda K minus 1, it should take K minus 1 vectors, tangent vectors V1 up to Vk minus 1, and gives us a real number. So each Vi is a tangent vector at M at the point x. We define this to be the following. Consider alpha of x. It's a K form. It's an element of lambda K T star of M at the point x. So if you give K vectors to this, it gives you a real number. Think about the V value of the vector field V at the point x and add the other K minus 1 vectors, V1 up to Vk minus 1. You get K tangent vectors. Alpha of x would act on that, it would give you a real number. So it completely characterizes what iota V of alpha is as a K minus 1 form. Okay, so that's how the interior product would work. Kind of the last subsection to discuss is the manifold version of pullback. We had pullback for vector spaces. So suppose we have two smooth manifolds M and N, and a smooth map F from M to N. For any K integer K, F star would define a map from K forms on N to K forms on M. It's important that the kind of direction of the arrow is changing. The map F was from M to N. F star is from K forms on N to K forms on M. So pick some K form on N called alpha. F star of alpha should be a K form on M. How can we define F star of alpha as a K form on M? Pick a point x in M. F star alpha of x should take K vectors, tangent vectors on M, and it should give us a real number. So each Vi is a vector tangent to M at the point x. How should I define this? Okay. Alpha is a K form on N, right? So alpha makes sense at a point in N. The input point would be f of x. Note that f is a map from M to N, so f of x is a point in N. Now look at derivative of f at x. It acts on Vi, would be a tangent vector at N. Up to derivative of f at x acting on Vk. Each of these vectors dfxvi, each of them is a tangent vector at N at the point f of x. Alpha is a K form on N. You can plug in K tangent vectors and N at the point f of x. It gives you a number. So we successfully defined what is f star at every point x. You see, that's how pullback of a K form is defined. We started with a K form on N. F star of alpha is a K form on N. The last thing to say is that if you pick a K form on N, F star of that is a K form on M, you can't take its D, it would be a K plus 1 form on M. Or you can first take D, it would be a K plus 1 form on N, and then apply the pullback F star. F star D of alpha would be a K plus 1 form on M. So you might wonder if it matters if you first apply D and then F star, or first F star and then D, and it doesn't matter. So F star, in fact, commutes with D. If you first take D and then F star, or first F star and then D, you get the same thing. Okay, it's a great place to stop.